Today we will learn magnetically coupled circuit and dot convention. So in the screen you can see the different magnetic coils. So what is a magnetically coupled circuit? When two or more coils are very close to each other, current in one coil will affect the EMF induced in the other coil. Then these coils are called mutually coupled or magnetically coupled circuits. As we know that the magnetic flux line always form a closed loop. The closed path followed by the flux line is called magnetic circuits. Thus, a magnetic circuits provide a path for flux, just as electrical circuits provide the path for the flow of electric current. So here we can see a magnetic circuit when coil 1, this is coil 1, this is coil 2, and they are placed very close to each other. Similarly, there are 4 figures, and these 2 coils are close to each other, and these 2 coils are close to each other. Now, what is a dot convention? Mutual inductance is a positive quantity, and we can get mutual inductance between this coil. Similarly, we have mutual inductance between this coil. We have mutual inductance between this coil. The mutual inductance is a positive quantity, but the sign of the EMF induced by it depends on the direction of winding of the coil. If you see a transformer core, here the winding is left to right. Here the winding is so this one is left to right, and this is same left to right. But winding can be right to left. Both are possible. So mutual inductance, as I said, this one is a positive quantity, but the sign of the EMF induced induced by it depends on the direction of winding of the coil. So in the circuit analysis, the dot convention is a convention used to denote the voltage polarity of the mutual inductance of the two components. So what is it? If two current are entering, see these two currents are entering to the dots. These two current are entering into the dots at the same time, then the voltage generated due to the mutual inductance will be positive. So that means here the M will be positive. The same thing when two current are entering all leaving. Here the current is leaving the dots. Current is leaving the dots. Then the mutual inductance will be positive. So in these two cases, that time current is entering the dots and current is leaving the dots. In this case, the polarity of the mutual inductance will be M will be positive. If say in the second figure, in this two figure we can see in one coil current is entering. This is entering in another current here. This one is leaving the dots. This is in one coil. This one is current is leaving the dots, and here the current is entering. So if one current is entering, all leaving the dots, and in the another current is leaving. When this one is leaving, the another is entering. Or when this one is entering and this one is leaving, that time the voltage generated due to the mutual inductance will be negative. Clear? So voltage induced here, this one will be V1. For this to figure, V1 is equal to, this is inductance L1, this is inductance L2, this is inductance L1, this is inductance L2. V1 will be L1 dI1 dt plus mutual inductance due to the current in the second coil M dI2 dt. And for this, similarly, V2 is equal to L2 dI2 dt L2 dI2 dt plus M dI1 dt. Now here this one V1, in both cases M is positive. M is positive, so V1 is equal to L1 dI1 dt minus M dI2 dt. This is V1. So V1 is the terminal voltage V1. This is V2. This was V1. This is V2. So V2 is equal to So V2 is equal to, this is L2. Sorry. This is L2. This is L1. V2 is equal to L2 di2 dt minus M di1 dt. So this is the expression. This is the expression of V1 and V2. So in any coil, we have to remember the expression of V1, that is the voltage of coil 1, this one is nothing but the terminal voltage. This is equal to voltage induced due to self-inductance plus voltage induced due to mutual inductance. Clear? Thank you for watching these videos. Please subscribe to this channel